Next we have Schween, and he is at the start of the.
No, it's not the first page.
Okay, get back to the start point.
Yes.
There we go. Okay, and they're going to be talking about Markov decision process dynamic programming for colloidal self-assembly optimal control. So thanks. Let's turn the time over to him now.
All right, good morning, everybody. My name is Tang from Georgia Institute of Technology. I'm doing research with Dr. Martha Grover. And today I'm going to talk about the Markov decision process-based dynamic programming for colloidal self-assembly optimal control. And first of all, I would like to talk about the motivation for our work. In this work, we aim to rapidly produce defect-free and grain boundary-free two-dimensional colloidal self-assembly crystals for the use of metamaterials. Metamaterials are materials made of periodically regular crystals, and they can be applied as semiconductors, chemical sensors, and photonic devices. However, the realization of these metamaterials require low-defect structural elements on small scales. And recent studies have found that using self-assembly of colloidal particles can provide a good solution to this miniaturization. However, there are two main challenges we have to overcome. The first one is without any external force, the system will take an infinite amount of time to settle into a fully ordered state. However, if you introduce some external force to accelerate the process, it will introduce defects easily, and it's very hard to get rid of these defects. Given these observations, we propose to use external electric force to accelerate the crystallization process, and at the same time, we are using the instant state information as the feedback to control the defects. And this project is composed by two parts, the actual laboratory experiments and also the math modeling part. And the experiment is set up at Johns Hopkins University, one of our collaborators. And in this container, there are 210 silicon dioxide particles suspended in the dialysed water in this container made of microscope glass slips. And there are 4 electrodes attached around this container to generate the electronic force inside the system. And the evolution of this whole system of the particles can be real-time monitored with the optimal microscope. And this figure just shows the simplified math modeling to simulate the actual experiments. Before we get into the details, I would like to give a brief review of the feedback control loop. To establish a feedback control problem, first you have to identify the process you want to control. And in this talk, we are going to control both the mathematical models and also the laboratory experiments. And the system today is captured with 2 order parameters we identified. One is RG and another is I6, which I'm going to talk about more later on. And the actuator we are going to use is the actual voltage generated by the electrodes to control the movement of the particles. And we use dynamic programming to calculate our control policies, with the objective to be driving the system to a desired order parameter we have identified. In a self-assembly colloidal system, the state space can be prohibitively large. And in order to construct our math model, we have to reduce the state space first. And in order to do this, we use diffusing mapping to reduce the state space. And the diffusing mapping is a technique that based on solving the eigenvalues of a transition matrix associated with some data set. And according to the resulting eigenvalue spectrum, it shows that we can reduce the state space into 2 dimensions. And by looking at the correlation with the diffusing mapping, we are able to identify 2 order parameters, RG and psi6, to reliably capture the dynamics of this system. And RG here is the radius of gyration. It can capture the condensation of this system. And psi6 captures the orientation of the bonds, therefore the existence of the grain boundary. Based on these definitions of these 2 order parameters, the objective in our control is to drive the system to a state that has a low RG value and at the same time have a high psi6 value. With this order parameter identified, we further on construct our stochastic models. First, we construct a Brownian dynamics simulation model by simulating the forces inside the container, inside the system. And the forces we considered in this BD simulation model include a drag force introduced by the particles moving in the solution, and a sprawling force due to the random collision of the particles, and also the non-hydrodynamic forces, which includes all the external forces. And the detailed information about the construction of BD simulation model can be found in this reference. But it's very computationally expensive to run massive BD simulations. So in order to resolve this problem, we constructed another model, non-driven dynamics model, to approximate the BD simulation. And in this non-driven simulation model, where X is the order parameter space, Rg, and psi 6, dx and wx are the diffusivity landscape and free energy landscape. And the data term here is the random noise required by the stochasticity. And this LD model has been validated against the BD simulation through mean first passage time. And the figure here shows a time distribution for the system to travel a certain amount of distance in the order parameter space under each of the 6 voltages that were used in our control. And the agreement between this mean first passage time validates the reliability of our LD simulation model to the BD simulation model. In order to use dynamic programming for our optimal control policy calculation, we further on simulate this process as a Markov decision process. An MDP is characterized by the set of time epoch T, the discretized state space S, and the actuator space A, and also the transition matrix PA. So the system state S is discretized by a DRG equal to 50 nanometer and a D psi 6 equal to 0.025. This is identified to most accurately capture the dynamics of the system evolution. And the control actuator's state space A contains of 6 different control voltages, where listed here, and with the capital V equal to 2 volts. And later on, we calculate the transition matrix based on the non-driven dynamic simulation data from 2070 distinct initial points, with each point simulated for 50 realizations. And we identify the jump time for the transition matrix to be dt equal to 10 seconds for the best accuracy. And then we constructed an infinite horizon MDP in order to get a time-independent control policy with the objective function given here as Ju. And in this equation, R is the one-stage reward function defined as the psi 6 squared, and the gamma is the discount factor equal to 0.99 required by the convergence of dynamic programming. And then we solve our optimal control policy by dynamic programming with a policy iteration algorithm. Before we get to the results, I would like to show the accuracy of our MC model. So in this figure shows a 100 realization average MC Markov to Monte Carlo simulation and LD simulation under different constant input A without any control policy. All of them starts from the same initial condition, which is a fluid-like state. And according to this comparison, we can see the MC is reasonably well approximate the LD simulation. And another point I would like to point out is, as the voltage increases, the system is able to achieve a better crystalline state, which is indicated by a lower Rg value and at the same time a higher psi 6 value. However, based on our experience with the experiments and also our simulation results, using a constant highest voltage does not guarantee the best crystalline state. And this is because under a highest voltage, the system is not able to correct for the defects during the process. And with this model, we eventually calculate our control policy with dynamic programming. And the counters here in this plots correspond to these 6 different control voltages from the lowest one indicated by action 1 and the highest voltage indicated by 6. In order to use this policy, you just look at the current value of the order parameter size 6 and the RG value and find the intersection of these two values and choose the corresponding counter as your control action for that moment. To evaluate the effectiveness of our control policy, we apply this control to our Markov chain model, to the Langevin dynamic simulation, and then to the Brownian dynamics. And we made a comparison between the controlled and the uncontrolled trajectory, starting from the same initial points. And again, all of these simulation results are an average over 1,000 realizations. And notice that the similarities between all of these three controlled trajectories once again validates the accuracy of our models. And also we have to notice that under control, all of the three systems shows a better final state than the uncontrolled highest possible crystalline state, indicated by lower RG value and also a higher size 6 value. To better understanding the control policy, we look into the time evolution of the order parameters for the controlled trajectories. And in this figure, we can see all of these three controlled systems give a similar trend to each other. However, there's a noticeable difference here. And this is due to the fact that out of these 1,000 realizations, the number of the trajectories that has used a non-constant voltage throughout the simulation time that differs from each other. This leads to the difference between this at this point in the size 6 trajectory. And we also, in order to study the control mechanism, we look into the average control policy which has been optimized under the control. And this figure again shows the 1,000 realization average, Monte Carlo simulation, Langevin dynamic simulation, and also the Brown dynamic simulation results. And all of them show a similar trend and features the point that you use the high voltage for most of the time. However, it features the use of low voltage at time of around 80 seconds. And this feature can be better visualized by looking at a single trajectory under control. And in this figure, I just plotted a single BD controlled realization with the optimal control policy that features the use of the low voltage at a state where has the low RG value and a low size 6 value. And at this point, the system got stuck in a place where it's very condensed, but it's disordered. And to correct these defects, the system chooses to use a low voltage to relax the system in order to reordering the particles in order to get rid of the defects. And once the defects are corrected, the system chooses to use a high voltage afterwards to get a finally better crystalline state. And given these results, we conclude that a Markov chain model is able to simulate the dynamics of the stochastic colloidal self-assembly process. And also with the control policy we calculated, we are able to achieve a green boundary-free crystalline state. And at this moment, we are still working on our models, our Langevin model, and Monte Carlo and Markov chain model, to get a better agreement in the control policies. And at the same time, we are trying to apply this control policy to the actual laboratory experience at Johns Hopkins University. And I would like to thank our funding source, National Science Foundation, and our research group, Dr. Martha Grover's group at Georgia Tech, and our collaborators, Mike Bevan's group at Johns Hopkins University, and Doug Ford's group at University of Massachusetts. And thanks for your time. Thank you.
Thank you, Jun. We have time for about 3 or 4 questions. So, any questions from the audience? Let me go ahead and just start with one. So if you can go back 1 slide, or 2 slides. Okay, so this shows the control action from the dynamic programming on the right, and the it either shows 6 volts or 1 volt. Was that surprising to you that you saw either the optimal control was either 6 or 1?
So if the control path is either 6 or 1, that's going to be a bonbon control, right? But because if you go back to this slide, if you use a very low voltage, which corresponds to 0.3 V, the system is not able to achieve a higher, to achieve a good crystalline state. That's why you want to use a high voltage for most of the time. However, as I said before, if you use the highest voltage the whole time, the system is easy to get stuck in a place where it's very condensed, but it's disordered. So we don't want to, so the use of a constant highest voltage does not guarantee the very well-ordered crystalline state. That's why we see this kind of control policy that uses a variety of different control voltages.
I think that's an interesting result. That
well, and you can see there's a little, just that very small rainbow region down at the bottom with the yellow and the red. So if you're too close to that final crystalline state, maybe you don't want to let off the gas completely. You just want to let off the gas a little bit. But most of the time, if you're getting stuck in a defect, you want to heal it as fast as possible. Maybe possible.
Yes.
So I understand this is an average. I guess your previous slide you were showing average trajectories over 1,000 realizations. So how much of a spread is there if you were to just plot all 1,000 trajectories on the same graph? Yeah,
that's a good point. I haven't done that yet, but I plan to plot the average also with all of the trajectories to see the span of this other parameter trajectory to see how the deviations are happen.
Most trajectories actually don't need any correction. So if you go to the next slide, you can see that voltage. The average voltage is almost always 1. It goes down to 0.85. So even in that 80-second region, most of the time, most trajectories are staying at 1 volt. So it's just a subset that gets stuck in the defects and need the correction.
Great. Time for maybe one last question. Okay, let's thank Shun and Georgia Tech again. And